Welcome back. Let's now start talking about linked lists. So linked lists, like lists, store a bunch of data. So here's a linked list where I'm storing 3 pieces of data, the name of 3 states, Maine, Idaho, and Utah. And like a list, it's just storing a bunch of information together in one data structure. Unlike a list, the affiliation between these data is a little bit looser, which I've rendered with these little arrows here. Okay, so let me tell you what the linked list composes of. The linked list composes of a bunch of nodes. That's one of these things right here. So here's a node, and here's a node. The node itself has 2 parts. The data being stored, in which case I've just put a string up here called Maine, Idaho, or Utah, and a pointer to the next item in the list. So it almost sounded a lot like a list. If I just stopped it, I'd have a bunch of data storing information, text, numbers, booleans, whatever it is. That would have been fine. Unlike a list, where the next item is sort of wired in based on the index, here in a linked list with this sort of looser affiliation, I have every node is responsible for pointing to who the next node in the list is. This is both going to be an advantage and a disadvantage for things like insertion, deletion, and access, as we'll see in a little bit. Okay? Now, linked lists are not built in. Lists are given to you in Python. You don't have to do anything special. Linked lists are not. We have to build it. So how do we build it? Well, we're going to build it using a class. Okay? So let's go ahead and build that, and then we're going to write some of the algorithms. So I'm going to define a class called node, and for now I'm just going to have the constructor. Okay? So I've got the constructor, underbar, underbar, init, underbar, underbar. There is self. That is, of course, going to be the address of the object that is initialized by the constructor. And you pass in a single parameter to this constructor, which is the data that you want to store in the node, Maine, Idaho, Utah. Okay? And all this constructor does is it says self, the object, a node, one of these things right here, dot data, that's where I'm going to store the information, equals whatever data you passed in, whatever the string is. And self.next, who is the next node in my list, it's going to set it to none. It's going to be empty for now. So the node is simply going to create one of these nodes, and then I'm going to wire everything up to create an actual linked list. Okay, so let's see what we have over here. So here's my little class. All it is a constructor. There's no member functions just yet. I'm going to define a node, and I'm going to call it head. That's going to be the first node in the list. And I'm going to do that by calling the constructor node, that's the name of the class, with the string main, and that will create one of these nodes where the data is the string main, and next is none. There's just nothing there. There's just a single node hanging out there, a little object in space. I'm going to create 2 more nodes, n1 and n2, calling the constructor with the string Idaho and then the string Utah. So at the end of these 3 lines of code, I've got 3 nodes, 3 objects hanging out in space. Okay, there's no notion of them being connected yet. Okay, so how do we connect them? Well, I want Maine to point to Idaho and Idaho to point to Utah. What does that mean to point to it? It means next should have the address of this node, and the next of this node should have the address of this node. Well, that should be pretty easy to do. So let's see. Head is this node right here. So I'm going to say head dot next is equal to whoever I want next in the list. So I want that to be n1. So now this element, this parameter here, this variable for this node is going to point to this node, n1. Okay, good. So I've now wired up the first 2 elements of the list. And then I want n1's next to be n2. So I want n1's next, that's Idaho, to point to the list Utah. So n1 next is equal to n2. And notice now I've wired up the list. So I've got a single node here called head. That is, in some ways, that's the entire list. That's all I need to know is the first item in the list, and then that points to the next item, and that points to the next item. So you can see why this is a looser affiliation of data, because, for example, if this node, Idaho, decides, I don't want anything to do with Utah, it can sever this, and then the list is gone. Every one of these nodes has, if you will, veto power to annihilate anybody downstream. You can't do that with a list. The 8th element in the list can't decide to annihilate the 9th element in the list. All those items are in the list. But here, because each one of these nodes is pointing to the next one, there's a little bit more volatility in this, and that's going to end up being an advantage and a disadvantage based on the algorithms that we're about to see. All right, so let's do a little manipulations of these lists to get comfortable with it. Let's say that I've created the list using the code on the previous slide, and now I just want to print every element of the linked list. Now, if I wanted to print every element of a list, I put a for loop for I in range length of the list, and I would print the ith element of every list. Easy to do. There is no notion here of indexing into a linked list. There is no 0th element, first element, second element. I mean, there's a first element, a second element, but there's no index into it. I've got to make my way through that list following these arrows or these links that I've created. So let's see how to do that. All right, so let's initialize a variable node to be head. So node now points to this object right here, which has main in the data, and it points to Idaho, which itself points to Utah. Let's not worry about the stopping condition on the while loop, and let me just go ahead and print node.data. So this is node, I reach in, I grab data, and I print main. Good. Now what do I want to do? I want to sort of move my way down the list. So I want node now to be this thing, because on the next iteration of this while loop of course is going to spin reading off each of the elements. I want node to be this. Well, how do I do that? So what's the line right here? Well, node, I'm done with this one, so I want the node to be, well, whatever's next. Oh, all right, so node equals node, this one, dot next. So now node will be this little guy right here. Good. So, oops, I think I did this. Okay, good. So node equals node.next, and now node is this object. And so again, let's not worry about the stopping condition. When I print node.data, it now will print Idaho. Good. So we print Idaho, we come back up to here, and now I'm going to say node equals node.next. So I'm going to go over to Utah, and then I'm going to come up, I'm going to print Utah, and then I'm going to come down, I'm going to say node equals node.next, and I get that guy right there, which is what? That's none. And it was none because in the constructor, all of the next variables were set to none. Here, I rewired the next variable to be Idaho, and here I rewired the next variable to be Utah, but this one is still none. So at this point, I'm done with the list. And so now, let's ask, well, what does it mean to be done with the list? When should the while loop stop? Well, the while loop should stop when the node is none, right? Because if the node is not none, well, then you have something there. And if it's none, it means you've hit the end of the list, because every one of these next variables has to point to something except for the last item. And so the stopping condition here is simply while node does not equal none, print the node data, node equals node.next, and then make your way. And this, by the way, looks a lot like the for loop. What's the difference? Is that instead of I equals I plus 1, I'm saying node equals node.next. So it's the same thing. A list is indexed on I equals 0, 1, 2, 3, 4, 5. A linked list, in order to make your way down, you have to keep updating what the node is using following the next variable, which are these little arrows here. So conceptually, it's exactly the same thing. It's just the mechanism is a little bit different. Good. So we're going to talk some more about deleting and insertion and access, but I want to give you some intuition about this first before we dive into the code and the runtime analysis. So let's imagine we have the same list as before, Maine, Idaho, Utah, so a linked list with 3 elements in it. That little slash there is the none, so there's nothing after this. And let's say I want to delete Idaho, right? So I have a pointer, a variable to Idaho, and I want to delete it. Now, in the list version, I would pull that out, and I would slide everything over. That was the expensive part, right? Because when I slide everything over, that's big O of n, because everybody's got to do a move into the previous sector position. But here, it seems because of this connectivity being loose, it should be easier. So how would I do this? Well, I've isolated this node, and what does it mean to delete it? All that I have to do to delete it is to take this next parameter right here in main and just override it to point to Utah. So instead of main pointing to Idaho, main is simply going to say, oh, you're out, so I'm going to just do a new vector here, and that item is now gone. And notice that that doesn't depend on how many items are on the list. Once I've isolated the node I want to delete, the fact that there's 1,000 nodes downstream is irrelevant to me. All I've got to do is take this next node and point it to here, and then those arrows keep moving. So the nodes themselves don't move, it's just the connectivity that changes. And so now you can see why this type of data structure with this loose affiliation of elements in the list is more nimble in terms of things like deletion, because I don't have to move things around. I just have to change their pointers, and that should be a lot cheaper. All right, so that is going to look like O of 1, because all I had to do was, once I find the node, I move the pointer from the previous node to this one. Everybody else downstream stays exactly where they are, and now deletion is not O of n, it's O of 1. That's nice. That's really nice. That's actually much, much more efficient, particularly if you have a dynamic data structure. All right, let's look at random access, and then we'll look at insertion and appending in the next segment. So let's say I want to access the third element in the list or the 10th element in the list. Well, unlike a list, I can't just move to that position. These things are just separate objects. They're all of type node. They don't really know about each other except through this next variable here. So if I want the ith object in the list, I've got to start at the beginning, count 0. Go to the next, count 1. Go to the next, count 2. Go to the next, count 3. And when I get to I have to stop. That is, I have to walk down the entire linked list until I get to the ith element, because notice there's no way of accessing that. Right? This is the head of the list. This is the variable for the entire list. Every other element in this linked list is accessible through these next pointers. I can't just simply skip down to some arbitrary position and go up the way I could in a list. So access in a linked list is expensive. It's big O of n. That's the price we're going to have to pay for that nimbleness and how these are connected. So there's an upside in terms of deletion, and as you'll see in a little bit, insertion and appending, but there's a big downside in terms of random access. Again, good, bad, it depends. If my database is largely about adding and removing things and I'm not doing a lot of random access into the ith position, well then I don't care that this is costly. But if I often have to grab the ith element, this is going to start to cost me. Okay? All right, so in the next segment we're going to do a drill. I'm going to have you write both insert and append, and then we're going to look at my solutions. And then we're going to talk about a variant of the linked list, which is called a doubly linked list, which is a slight variant of it that allows us a little bit more power and flexibility in manipulating these. So when we come back, please be ready to do a drill, and we'll pick it up in a few minutes.